Welcome back to another video for high school chemistry. Today we're going to talk about periodic trends. First off, what is a trend? What do you think a periodic trend is? So a trend is something that shows a pattern, something that goes forward, something that kind of shows us where something is going. There's fashion trends, there's technological trends, there's historical trends. Periodic trends are how elements behave as you move across a row or down a column, and how they change and what similarities they are and what you can predict. It's all about being predictive in chemistry and with periodic trends. So first, we're going to talk about each of the regions of the periodic table. The first one is the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. So these are trends based on a column, kind of behavior of that column. All the alkali metals have one valence electron. They all have this in common. And what that does is it actually means they behave similarly. So they're never found pure in nature. It's because they're too reactive. You can have lithium chloride, but not pure lithium metal in nature. They react with oxygen in the air, they react with water, they react with all kinds of things. The reactivity of these elements increases as you go down. So cesium is way more reactive than lithium or sodium. So a lot of them look like shiny silver metals. They actually have to be stored under oil typically. And potassium here, it reacts with water and has to be stored in kerosene or oil or something like that to keep it from reacting explosively with water in the air. Alkaline earth metals. Alkaline earth metals are the next column: beryllium, magnesium, calcium, strontium, barium, and radium. All the alkaline earth metals have those two valence electrons. They are less reactive than the alkali metals. However, they still cannot be found pure in nature because they're too reactive. The word alkaline means basic because the most common salts of these and many common bases are salts of these metals. So calcium hydroxide, magnesium hydroxide, as well as calcium carbonate is an alkaline or basic substance. You may know calcium carbonate better by the name limestone or chalk. So properties of metals. So these are all metals. There's lots of metals on the periodic table, actually more metals than anything else. Metals are good conductors of heat and electricity. It has to do with how their electrons are arranged. They're malleable, means you can hammer them into a sheet. They're ductile, which means you can draw them into a wire. They have high tensile strength, means they're very strong and hard to break apart. They have luster, which means they're shiny. This is a gold plating on Tutankhamun's mask, showing the gold is still shiny after all of these years. Transition metals, all those ones in the middle are considered transition metals. Copper is one of them. It's relatively soft metal. It's good electrical conductor. You have mercury, which is the only metal that exists as a liquid at room temperature. There's metalloids, so there's a stair step going down the periodic table. You have boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. They have properties of both metals and nonmetals. They behave a little bit like both, and depending upon which one as to how they behave more. Metalloids are more brittle than metals, but less brittle than most nonmetallic solids. They're semiconductors of electricity. And so that means that they get used in computer chips and in the computer industry a lot. That means instead of conducting electricity all the time, they only conduct electricity when they get hot. Some metalloids possess metallic luster. Silicon in particular, it has metallic luster. It's brittle like a nonmetal. It's a semiconductor of electricity. It gets used in Pentium chips and in other silicon computer chips. This is a Pentium 4, hilarious. We're now up to like the i7 10th generation or something like that. Other metalloids are boron, germanium, arsenic, antimony, and tellurium. The nonmetals. Nonmetals are poor conductors of heat and electricity. Nonmetals tend to be brittle if they're solids. Many nonmetals are gases at room temperature. So nitrogen, oxygen are gases at room temperature. The carbon, the graphite in a pencil is a great example of a non-metallic element. So there's also sulfur, which used to be known as brimstone. There's microspheres of phosphorus, which are a reactive nonmetal. Graphite isn't the only pure form of carbon. We also have diamonds, which are a pure form of carbon, and some of the impurities in that will give us different colors and things. So halogens, also nonmetals, but have their own separate subcategory called the halogens. They all have 7 valence electrons. They are never found pure in nature because they're also very, very reactive. And in their pure form, they're always diatomic, which means there's always 2 of them together. So F2, Cl2, Br2, and I2. Fluorine and chlorine are both gases. Bromine is a liquid at room temperature. Iodine is a solid. Acetine is also a solid but unstable. Noble gases, last column in the periodic table. These have 8 valence electrons, except helium, which only has 2. It's because it's in the first shell. All of them have filled, happy shells of electrons. The noble gases are only found pure in nature because they're so unreactive. They're colorless, odorless, and unreactive. They were among the last natural elements to be discovered because of the fact that they are so unreactive. They're hard to track down and make react with things so we can learn about them. So, periodic trends. Here's a chart that shows the atomic radius as a function of atomic number. You can see it goes down and then goes back up and then down and then back up and then down. So this is atomic radius. The atomic radius is defined as half the distance between the nuclei in covalently bonded diatomic molecules. So you have two atoms together and they're stuck together. What's the radius between them? So the radius decreases as you go across a row or a period. There's increased effective nuclear charge, so as you go across you get more protons in the middle, and what that does is it means the outer electrons feel more positive charge that way. The radius increases as you go down a group. So when you go down a group, this is because each row in the periodic table adds another shell of electrons, and so that's why you see that big jump in radius, is because there's another shell of electrons being added. But then as you go across, you get what feels to the outer electrons like more and more positive charge, because you're increasing the positive charge, and it pulls them in a little bit tighter as you go across. The atomic radius decreases as you go across, and the atomic radius increases as you go down. Same thing here. I really recommend drawing a sketch of the periodic table and writing in these arrows as well as the words to help you remember them. So ionization energy is the energy required to remove an electron from an atom. So it tends to increase across a period. So as you go across a row, it gets harder and harder to remove an electron. This is because as the radius decreases across a period, the electrons are moving closer and closer to the nucleus, and they're therefore harder to remove. Because remember, they're negatively charged, the nucleus is positively charged, so the closer they get together, the harder it is to pull them apart. And they tend to decrease as you go down a group because you're throwing on another shell of electrons, so it gets much bigger, and those outer electrons are much farther away, so usually easier to remove. Again, ionization energy increases as you go across and decreases as you go down. Electronegativity. Electronegativity is defined as a measure of the ability of an atom in a chemical compound to attract electrons. So this is how much it wants more electrons. So electronegativity tends to increase as you go across, opposite of ionization energy. And as radius decreases, the electrons get closer to the bonding atom's nucleus. Electronegativity tends to decrease as you go down or remain the same. It's because the closer it can get to the nucleus, the more likely it is to get to the nucleus. So as radius increases, electrons are farther from the bonding atom's nucleus. So here is a chart of the electronegativities. You'll notice the noble gases aren't on here because the noble gases don't really want to ever gain more electrons. because they're stable and unreactive. So they tend to not come into electronegativity charts. But you'll notice fluorine is by far the highest. The most electronegative elements are fluorine, oxygen, nitrogen, and chlorine. And you'll notice that generally speaking, francium, radon, these over here, are the lowest electronegativity. So electronegativity increases as you go towards fluorine, which has the highest electronegativity. So electronegativity increases across, decreases as you go down. So here's a summary of all of those periodic trends. Atomic radius decreases, ionization energy increases, and electronegativity increases as you go across. Atomic radius increases as you go down, ionization energy decreases, and electronegativity decreases as you go down. Ionic radii. So this is ions. When atoms lose or gain electrons, we can get cations or anions. So cations are positively charged ions that are formed when an atom of a metal loses one or more electrons. So a cation is positive. They're smaller than the corresponding atoms. So when you let go of those electrons, you end up dropping down to a lower subshell, and so you end up with a smaller radius. Anions are negatively charged ions that are formed when a non-metallic atom gains one or more electrons, which means that the radius increases because there's more negative electrons in that outer shell. So larger than the corresponding atom. So here is a comparison of the sizes of atoms and their ions. So you'll notice that the lithium ion is smaller than lithium without a charge, but then you go over to the right to fluorine and you'll see that fluorine itself is much smaller than the fluorine anion, also known as fluoride.